So atomic spectroscopy. Anna, which machine is that upstairs? Your favorite one?
They haven't done that one yet.
We like it.
Everyone's had experience on every machine. Well, the first half of the lab.
Yeah.
All right.
I haven't done GC.
Remember, I was asking about the
You guys
lab.
haven't started GC yet?
I haven't done GC and they haven't done FTI.
We haven't been.
Oh, I thought we did a complete rotation. Oh. Okay. Guess not. But the AA is the one that uses the flame. Right. Okay, so we're going to break up AA into two parts. This is our first part. Do you remember doing anything like this in lab, Pablo, where you had this little metal loop, and then you dipped it in different metal solutions, then you put it in a flame, right? And then you saw this stuff, right? So was that atomic absorption spectroscopy? It's emission. Atomic emission spectroscopy is what that was, right? It's emitting light. Okay. But it's the same, really, idea. I mean, if it emits that little narrow range of blue, it'll absorb that little narrow range of blue. Okay. At room temperature in a dilute solution of sodium and chloride, the sodium and chloride ions, Sandy, are in their blank state. In their what? Ground state, yeah. Okay. Now, since we're in this nice room and you guys are all comfortable, you're Andy, we don't have a flame outlet. That flame outlet is what gas, by the way? Methane. Is that what makes the smell?
No, it's the stuff you put in it.
Yeah, they put, what type of compound? Sulfur compound, yeah. Anyway, so we don't have that in here, so we just have to go by the folks who did make up dilute sodium chloride solutions, put them in the AA, hopefully looked at the flame, and they saw what color? Orangish, right? This one right there, right? Right there, right? Kind of yellowish, orangish. Probably more yellowish than that. Might even be more like this one. Oh, they both kind of look the same. Adriana, we've had that discharge lamp, and we've looked at it through little spectroscopes, and we saw all the little lines. I don't think we saw as much as this. I mean, this is like a monochromator with a detector head, almost give us that, or a photographic plate or something. But why do atoms in a hot gaseous medium produce line spectra? Now there's a couple hints here. Okay, now first not molecules. Atoms. Now what kind of atoms? They have to be metallic, right? Pretty much metallic atoms, right? Is what we're kind of talking about. Because it seems to work the best. Because if you take something like oxygen, it's not going to stay O atoms for long. It's going to make O2, and it'll be something else, right? So we want line spectra. So we need atoms. So that's why this word is worded. This question is worded the way it is. Has to be atoms, because only atoms are going to generate lines. Why would that be? Ricky, why would atoms produce line spectra, whereas molecules don't? The big hint is that big, complicated, it's called a Jablonski diagram that we did last time, where we had that letter E that you were complaining about. There's no E.
Does it? I can't
Right.
believe you agree with him.
I'm not agreeing.
No. Is it because they have their own electrons that aren't being shared with other atoms in a molecule?
Remember, not really. Okay, to produce a line, right, you have to have a ground state. You can have all these other states, singlet, triplet states, all that kind of stuff. But the point is these were these dark lines, and then we had little tiny thin lines. Remember this? What was the difference between the dark lines and really tiny thin lines? Oh yeah, yeah. Everything up here was excited, and everything down here was ground. Vibrational states. Can atoms, Emily, have a vibrational state? An atom? How would you make an atom? Right? There's no bond to vibrate. You're not going to have these. Right? You're going to produce very narrow lines. Okay? So it's simpler. It's less complicated than a molecule. You can't have so much going on. The energy can't be dispersed in so many different modes and all that kind of stuff. Okay? And the whole idea of it being gaseous, well, it has to be a gas, because if it's not a gas, right, you're not going to have atoms. If you're not going to have the atoms, you're not going to get the line spectra. Right?
They don't vibrate, they just go from nyat to nyat.
Yep.
All right.
Yeah. Nyat 1 and nyat 2. Okay? Are we okay so far? Okay.
There's no, when you're dealing with the atoms, there's no vibration.
Mm-mm.
It's just from ground to
Yeah.
state.
Yeah. And we're simplified. I'm sure there's more than 2 states here for their atoms, but that's essentially it. Okay? So, sketch a general absorption spectrum of solution containing molecules. So, Sir Rico, have you done the UV Viz yet? Nope. You've done the UV Viz, right, Alice?
Yeah.
That's the very first lap. So, it was what versus what? Do you remember the axes? When you got an absorbance spectrum? Yeah, absorbance versus wavelength. And then what did a typical absorbance spectrum look like? Yeah, do you see what she said? A curve, and then she drew her hand down again, something like this, right? You can draw any blob you really want, right? Okay. Sketch a general absorption spectrum of an atom. Emily, would it be the same axes? Absorbance versus, yeah, it's an absorbance spectrum, so it has to be, right? Okay. What would it look like? Robert, what would it look like? Lines. Yeah. Boom, 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 boom. Right? Okay. Atomic spectra are actual lines, but they do have some narrow width. So, I mean, we could really zoom up on this, and you'd see, oh, well, here's your line, but there's a little tiny bit of something going on there, right? There's a little tiny width going on there. Okay. How can there be some width on it? I mean, you're going from this excited state to that ground state. There's no width there. What have to do with? Well, that would have, yeah, that's going to have effect on.
Oh, that's that atom broadening.
Zone broadening or whatever? Why am I trying to read yours?
Pressure broadening. Ooh, that'll give it some width. And also Doppler, and also the
Oh, Doppler, that was in the radiation.
uncertainty principle. Okay, now, see, Pablo's not in PChem, but Adriana is. Please explain the uncertainty principle to poor Pablo.
We don't know anything.
That's okay.
Just Google it.
We cannot know the momentum.
Put it this way. Do you remember? Pretty much, Pablo. It's like if you're playing baseball on the tabletop versus baseball inside a molecule, right? You have the little electron. So you could do a little, yeah, kind of, yeah, trajectory, right? And if you're hitting baseball here on this tabletop, you can see the ball flying. But if it was inside a molecule, all you know is that you could hear the hit of the bat and then the smack of the glove. You have no idea how it got from there to there. No idea. Okay. Now, if you want to narrow it down, how it got there, then this gets wider and wider and wider. So there's this playoff that you got to work with. But the point is that you never really know anything for certain. Everything's probability. So drawing a single line there and a single line there is extremely, extremely misleading. In fact, it's wrong, according to quantum mechanics, right? Which only works, and it hasn't been proven wrong for what type of world? The microscopic, where things are quantized world, right? Really, really tiny. Okay. So it's misleading. So that leads to some line width, right? That where is this energy? Is it here? Is it here? Is it here? Right? Oh, there's a little uncertainty there. But the probability is highest right in that very center there. Okay. Let's jump down to, Doppler broadening. Okay. Who's had PChem? Sandy, you had PChem? Not PChem. You had general physics. Yes? Okay, well, come on up. Before I have you come on up and explain, well, you can try it, right? Okay, have you heard of Doppler broadening? No? Who remembers Doppler broadening from general physics? All right.
Yeah, exactly.
Now, this can almost reach you. Slide this over a little bit, Ashley. Robert, get up. Get up, get up, get up. Okay, Robert's going to demonstrate the Doppler effect to you. So I turned this thing on to the most nauseating sound I could find. That's probably not loud enough, though, right?
No, that's plenty loud. Son of a...
Okay. So this frequency is exactly 7.53 kilohertz.
I can only hear it on one side.
Okay? He's going to demonstrate the Doppler effect. How? Here, take it. You can do it. Big guy.
No, I can only hear it on one side. So. Why don't you just kind of get up? Yeah. Right there's that. Right
That's
there's
intensity.
Bad.
That's intensity, dude. What do you got to do to get Doppler broadening? You have to change the frequency. I can change the knob, but Doppler broadening doesn't let you touch the knob. You have to do what with it? Right? Frequency definitely changed. It physically changed. What I was hoping you do, Sir Robert, is this. Right? So, what does that have to do with making this wider? Atoms are moving, right? They're moving. Okay, so think of it this way. Let's focus on emission because it's easier to imagine, I think. You have this atom, right? It's supposed to emit exactly this wavelength, right? And let's say that's green. I don't know, right? It's that green line, really dark, deep green line, okay? But this little atom, he's in that hot gaseous medium. He's an individual atom, and he's flying right towards Alice, right? According to the little atom, if he can see himself, he emits green light. But he's going toward Alice, so what color does Alice observe? A higher frequency or a lower frequency?
Higher.
Oh, we gotta do this again. All right, I'll try to find a less nauseating frequency. I would hear Robert complain. All right, now I'm not gonna hit you. Where does it get higher frequency, when it's going towards you or away from you? Towards. Okay, so let's go back to the story here. Think of it this way, Roy G. Biv. Pick a color, Alice, that you would see then. According to the atom, it's emitting green, but it's flying right at you. What color could it make it out to be for you? Yeah, she has to go to blue shift is the technical jargon. It's going to get blue shifted on her. Okay? Same dang atom, supposed to emit that lime green that your Andy's wearing, right? But it's flying away from Rico. So, John, what color would you see? Possibly. Yeah, it could be yellow or orange or red. It's red shifted because it's moving away from you. So, just these atoms flying around, just what color are they emitting? You can't stop them from, you can't stop the Doppler effect. So, there's a cause for widening. And what enhances it? Dang, you could make things move faster, pressure broadening, and it just kind of worsens things. Okay, they get in the way, they slam into each other, and then you get collisions and you get more effects going on, and this gets even worse. Okay? And you get self-absorption with pressure broadening. He emits green, but another atom absorbs it before you even see it. So there's some problems there. But those are the three.
What the heck is pressure broadening then?
Okay, think of pressure broadening. We need an animation. We need a movie. We need a movie because showing how you have little atoms flying around, right? And just a few, really dilute, right? And then you show the spectrum. You get a nice green, these individual lines, right? And then you start slamming in more and more atoms. So they're colliding with each other really, really hard and very, very often. And then that little green line starts getting fuzzy. You start seeing them move around. Oh, is it here? Is it here? Is it here? Right? It's not really, because there's different shades of green. So it's this thing, right? It's getting wider. So it's this line bouncing up and down, or this one, or both. So and then you also have self-absorption makes it worse because you want to see green light. That's the whole purpose of this lamp that you build, that discharge lamp. Well, if we had a really high pressure in there, one atom emits it, but then another one will just absorb it. And that, just the probability of that happening increases. It's called self-absorption. So that's also a negative thing. Okay. Atomic, but self-absorption really isn't. I'm worried more about those three. That's what gives the width to line spectra. Atomic absorption versus atomic emission spectroscopy. Oh, let's pick on somebody. Adrian, picked on.
Yeah, get her again.
Who haven't I picked on in a while? Nico. Emily! I haven't picked on Emily. Emily, go ahead and read this. Read this. Well, I'm picking on you again. Read the fact.
Atomic absorption spectroscopy works with a very large population of atoms in the ground state. In fact, the temperature of the flame, 99.9% of atoms are in the ground state. Atomic emission spectroscopy works with a small proportion. Only 0.017% of the atoms are in their excited state.
Isn't that kind of weird? Right? I think it's weird because you think of a flame, you think of something that's really, really hot, right? But we're talking about metal. It's not hot for a metal. I mean, they're in their ground state. Only 0.017%. 0.0017 fraction is in the excited state. So very small number of them are even have the energy to emit, right? Very, very small amount. Which method then, Robert, do you think is the most sensitive technique for quantitating metals? What's quantitating? Not identifying. Just finding out how much. To quantitate something, you have to know what it is. Otherwise, how would you figure out how much? All right? Okay, anyway. Which method do you think is the most sensitive, Anna? Would it be atomic emission or atomic absorption? With this, given this little fact. Right? It would make sense for it to be atomic absorption. However, let's see if I can show you something here. Yeah, I set you up. We need a black page. Okay. So, hang on. I don't want you to look over here. Look over here. Let's do absorption spectroscopy first. see, how can I? Okay, let's do a absorption spectroscopy first. Absorption is the negative log of what over what? PO over P. Okay, what's PO again? Incident. Whatever. You want to distinguish between those two, right? I said negative log. So, right? So you want to distinguish between those two. So what's the difference between these two? What are they in the first place? What are these P's? Incident and transmitted, but what? Intensities of light, right? That came from the what? Monochromator, right? Because it's a single wavelength. Make sense so far? Okay, here's an absorbance measurement. Okay, here's your incident intensity, right? And then here's your transmitted intensity. Incident, transmitted. Okay? Just remember how sensitive that was. See, you could tell the difference, right?
Yeah.
Where'd my little bag go? Here it is. Okay. Emission spectroscopy. Problem is, this room needs to be black. So the only way to make it black is, here it is. Flashlight's not on. This is your background. This is your background. All right? You can't see anything. Here's your signal. There's your signal. There's your background. There's your signal. Now this would be much more dramatic if I could have all the lights off in this room, because that's what it needs to be. That's what emission spectroscopy is. Which one's more sensitive? This one. There's no background. I mean, there's much, extremely less intense. I mean, there's hardly any light here at all in comparison to that absorbance measurement. But it's so much easier to measure. Well, that's what sensitivity is, right? What's easier to measure? Emission spectroscopy, because of the background, right? So, Pablo, does that make sense?
Good question.
Because of the background.
Yeah, really, yeah, that's pretty much it. Okay, Sandy. Where are we? We're right here. We want absorption to occur when doing AA spectroscopy, because we're not doing AE, we're doing AA, right? Atomic absorption spectroscopy. We want absorption to occur. So why do AA spectrophotometers use a flame? Who am I picking up? Sandy. Does anybody have an idea? This is what we want. I mean, this is coming from the light source. Because if you want to study sodium, you have to have a what lamp? Sodium lamp, right? If you want to analyze for copper, you have to have a copper lamp. Okay, so copper absorbs copper light, so you have to have a copper lamp. So I'll just say that's copper. Okay. Well, if you want to, you go to the AA cookbook, and it says, okay, in this range, this slit width, and all this blah, 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 it wants you to use this wavelength right there. I'm just picking it, okay, for whatever reasons. And they go through a lot of analysis to see which line gives the most sensitive or which line gives the most linear response. And they go through a lot of testing. So that's why you follow the cookbook. A lot of it. Most AA plots aren't even linear. But that's why you have to follow the cookbook. Anyway, so you pick this line. So the lamp, the copper lamp, is kicking out that line. The monochromator is set to it. Whatever's in copper in the lamp is an atom, right? Hot, gaseous, medium. It's pretty much kind of like that matrix idea, right? You got to have copper atoms, because only copper atoms are going to absorb that line. So if you have it in the liquid, it's not going to work. That's not copper. You know, if copper ions are dissolved in water, they're not going to absorb this line. Only copper atoms in a hot gaseous medium emit that line. So only copper atoms in a hot gaseous medium are going to absorb that line. The best description, I think, for this is, what is a flame? Atomizer. That's the whole purpose of the flame. Because you can't have anything else. It has to be whatever's inside that lamp that's generating the light in the first place. And those are atoms. So you have to have atoms, otherwise it's not going to absorb. Whether it's copper, sodium, or whatever. That flame is our atomizer.
So you're just trying to match the matrix?
Pretty much. And there really isn't a matrix. I mean, you're really trying to match what emitted the light in the first place. And what emitted the light in the first place? It was a dang atom. Not an atom stuck to another something. Not an ion either. It wasn't Cu plus that emitted that light. It was Cu. So you have to have Cu in the flame. Atoms. You can't have Cu plus. You can't have Cu plus 2. No. It has to be Cu. Atoms. That's what's going to absorb the light. So you have to match it exactly. So it's an atomizer, not an ionizer. No, you got to make atoms, not ions. How does our AA introduce a sample into the flame? Okay. Where was that?
Sample capillary.
Yeah, there's that. What color is this little tube for those of you who have done the AA?
Hopefully transparent.
Yeah, it is transparent, clear.
I thought it was white.
Well, yeah.
It's a white clear.
Yeah, a little white Teflon tube, right? Polyethylene or something, right? It was a white tube. I thought it was white. I don't think it was clear. I don't remember.
We're trying to see.
Opaque. All right? But that's a little tube hanging out of the thing. So here's the major components. But why does it suck it up in the first place?
So that it can get up in.
But how? There's nowhere in here does it say the word pump.
So it can go to the nebulizer.
Yeah.
There is a nebulizer.
But what is causing, right? Here's your little beaker. It's full of liquid. It's in there, right? The capillary tube. What's causing it to suck it up? Pressure. You're getting there,
Flaming
It's a vacuum pump.
right?
thing? Yeah.
The answer, I think, is really, well, it's the Bernoulli effect. And the next step is the Bernoulli effect is exactly the same reason why what fly? Airplanes. Now, why do airplanes fly? Lift.
Pressure on the wings.
What's lift?
Pressure on the bottom, higher than
Yeah.
pressure on the
Yeah.
top.
Very important match.
Pressure on the bottom is higher than the pressure on the top. But it has to be generated. I don't see any big pumps out there on those wings. What's the shape of a wing? It's
More
what?
surface on top, right?
There's more surface on top
And that's
and less on the bottom. Okay? That's my wing. Does the wing move through the air, or does the air move over the wing? What I mean is, you take off from San Antonio, you fly to Austin. Does that air move with you, or does the plane fly through the air? You get out of Austin and that plane around, the air around the wing is San Antonio air? Or is it Austin air?
Is that Austin there?
It's Austin air, right? The plane moves through the air, right? So this guy is moving, right? Air's going around it. Whoosh, 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 whoosh. Right? Which one does it have further to fly? So which one, on top of the wing or on the bottom of the wing, does it have further to go?
Top one.
Why?
Because there's a curve.
More distance. Same amount of time. If it's, right? Whether you're on the starting down here or up here, you have to get to this point at the same time. You have to, because you just said you don't end up in Austin with San Antonio air. So, see what I'm saying? They have to both That air has to stay here. That air has to stay in San Antonio. So the wing goes through the air. So it has to travel on top faster because more distance. Okay, what does that have to do with anything?
Doesn't that create less pressure?
Has to travel faster?
The top has to travel faster.
Because it has
Like
more
the top
distance.
The air on top has to travel faster. So fast-moving air does what? What's so special about fast-moving air? It's what? Has something to do with pressure. All right, let's see if you can picture this. I'm going to blow as hard as I can on the top of this card, right? If I blow on it, it just blows away, right? But if I blow on it in such a way that the air is just dispersed on the top of the card, so I have to blow through a little tube, right? I'm going to put that on there, blow through this guy. The air is going to be dispersed totally on that card. It's flat on its surface. Just like it would be on top of the wing, it's moving faster than it is down here. Because I'm not going like this or anything down here. So the air is just moving faster on top than it is on the bottom. Less pressure. Less pressure generates the L word, lift. Because it's what Ricky said in the beginning. There's got to be a pressure difference. There has to be more pressure down here than there is up there. Somehow you got to generate it. You generate it through the whose effect? Bernoulli. Right? And if this doesn't work, every plane in the sky has to fall out right now.
It's being held up by God.
All right?
Wait for our lungs to fill up again.
Okay. Okay, now just to finish my story about airplanes, does anyone in here, believe they can win the lottery? Go buy a lottery ticket. No one has ever bought a lottery ticket in here?
I think
No, I have never bought a lottery ticket.
do the math, it's pretty simple.
Okay. Now, has anyone ever bought a lottery ticket? Okay. Did you have an honest belief that you thought you could win? Oh, come on, you had to have some little inkling. There has to be some chance, right? Right? You had to believe that. Otherwise, you wouldn't have bought it. Make sense? Okay. You go in the airplane. You know the loudest spots where the big engine jet, the propeller. It's got a very weird blade, right? Those turbines, and you look in there, it's got the really thin blades in there, all right? Yeah. Sit next to that guy, right? The statistics are it's about the same as winning the lottery. That a turbine, a blade, is going to get knocked out of place, right? And go through the window. It happened. This lady was sitting next to her little boy, right? But that's the odds of it. And that's the only reason why I know the statistics is because I read the article that the thing failed, but nothing really happened because you can't redesign these things. It's just statistically that's how it is. It's very safe. Very, 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 very safe. So why buy a lottery ticket, right? You're not going to win. Because if you're going to sit in an airplane, sit next to the turbine,
I will buy all
right? It's the same idea. Same odds of dying. All righty. That's my airplane story.